this done? Nice. Okay. Now it is a little bit of concern to me to know why this a lot of people are stopped coming, because if I am doing something that people don't need, then I'd rather not be doing it. Okay. But anyway, there could be lots of reasons. Now I am going to today try to complete the basics of supersymmetry, which I started teaching 2 lectures ago. So this is the 5th lecture of the course, and so these 3 lectures today and last 2 together would be a kind of mini introduction to 4-dimensional supersymmetry. Now this is not a conceptually difficult subject, but technically it's pretty hard. Already we've seen that some of the stuff one has to do requires some unfamiliar manipulations. And today I'm going to complete it, and it's going to be harder still, and there's not much chance that anybody will benefit from today's lecture unless A, they already know it, or B, they're really going to spend during the next 3-4 days at least like 4 to 5 hours working out details. Okay, so I'm just telling you that I'll do it anyway, but if you expect to get something out of this lecture, particularly today, you need to do some hard work afterwards. Okay. Good. So last time our conclusion could be summarized by saying that the free action for a single chiral superfield is integral d for x over everything, integral d2 theta dagger phi plus integral d2 theta phi squared and the half m plus cc. And we worked out in detail that this gives, first of all, an ordinary space Lagrangian involving a scalar field, a fermion, and auxiliary field. That Lagrangian eventually looked like, I'll write it anyway because this will be useful. It first of all looked like this plus this plus f star remember that plus ff star is a sort of wrong sign, because if you think of this as a potential, part of the potential, it's a negative term in the potential. Okay, but we'll see that after we eliminate the auxiliary fields, then we'll get things with the right sign. So auxiliary fields typically have that property that they occur with the wrong sign. That does require a little bit of gymnastics, because it means the Gaussian integral we do in Euclidean continuation would be like e to the plus f squared instead of e to the minus f squared, which is not at all the same thing. Okay. But we follow the practical approach and just assume that you can integrate out these fields. In addition to this, we got half m times 2 phi f minus psi and its complex conjugate. And this thing, after integrating out f, the auxiliary field, then reduces to a more familiar form. And then minus m squared phi star phi minus half m there's not much content in m being complex, because as you see, its phase part doesn't appear here, and here it can be absorbed by an opportune redefinition of psi, okay, and an opposite redefinition of psi dagger. So these constant phases in psi and psi dagger will not affect the kinetic term because it has a psi and a psi dagger, and here they can be used to absorb the phase in M. If you think back, you'll realize that this is part of the story of the CKM matrix. We saw that the most general mixing term, if you have multiple fermions, can be removed up to a few possible phases, but here we haven't even assumed mixing. Here we are in the 1 by 1 case. There I tackled the 2 by 2 and 3 by 3 cases, and there I showed you that in 2 by 2 case you can remove all phases, and in 3 by 3 there's one phase which is CP violating. Surely in 1 by 1 case you can remove all phases. So that's the statement that we can make M clear. Is that point clear?
Sir,
yes.
Last time we did do the detail. So by dagger phi, how does it give this kinetic term?
Last time we didn't do what term? This one? Very good. So what's happened is that in my mind, I assumed that I had reached, you're absolutely right. This is a consequence of the very stressful morning I had today. And you're absolutely right, thank you. So we are going to, you're absolutely right. We didn't reach this result last time. By the way, did anybody else notice this fact or only him? Oh, you did notice, I'm so glad. Okay, well, there was no harm telling me. So I'll do it now. This is the answer. So now you can see that I'm basically summarizing that this is what we'll get. What of it did I already get for you? I already got this line and this line. What I didn't get is this line. Okay, that's because this line and this line come from here, but the top line comes from there. We did give an argument last time that this will give rise to the kinetic term and this will give rise to a mass term. All these terms you see have, okay, so actually what I didn't get for you is this and this term, all of which will come from the top line. So let's do that calculation now. Okay, so thanks very much. Calculation of the D term. Okay, so for this we have to notice that phi dagger phi is really phi dagger of y dagger and theta dagger and phi of y and theta. Okay, now since both y and y dagger are going to appear under the d for x sign, there is no chance to shift away both of them to become x. We could at most have shifted one of them to become x, but we needn't even try to shift. Since we can't do it, the correct strategy is just to take phi and phi dagger and expand them out by expanding them as functions of theta dagger and theta respectively, and then also expanding out y as a function of theta and theta dagger. So expand them out until we finally get a function of x, theta and theta dagger. However, it won't be the most general function because it still satisfies the chirality constraint, and it's quite easy to show that phi of y and theta is equal to small phi of x. You will see exactly how these terms arise. It's almost obvious by inspection. I won't always be writing the argument x, but everything depends on x. So let's understand why this happens. If you look at this, you'll recognize that I have written it in perhaps a very clear ordering, in the sense here is 0th order in theta. Was there some correction? Okay. Here is 0th order in theta, here is 1st order in theta. Okay. 2nd order in theta is here as well as there. 3rd order in theta is here, and 4th order in theta is here. Okay. But there might have been more terms in general which are not here. For example, there is no term involving theta dagger, theta dagger. Okay. Why is that? It's pretty obvious. If there were a term involving theta dagger, it could never come from expanding a function of y and theta, because the theta is just theta, while y depends on theta and theta dagger equally. So you can't get theta dagger squared without a theta squared. So this is actually what you get. Okay, and this is one way among many to see that a chiral superfield is necessarily complex. You can't make it real. Okay, if you make it real, what will happen? You'll have to add this to its complex conjugate. But this is chiral and its conjugate is anti-chiral, so the sum of them is neither. Okay, so I hope that point is clear. And you can see now that something I had said last time, that the independent fields in this expansion are phi, psi and f. There are other places where fields occur, but those fields are all defined in terms of phi, psi and f, namely derivative of psi and derivatives of phi. Okay. And I suppose it's also obvious that this term comes from having phi of y. This small phi could have been a function of y, obtained by taking this and setting this theta equals 0. But then if I expand that y back in x, then I get this term and this term and this term. It's right in front of your eyes. Okay? Then I would have got root 2 theta psi of y, but if I expand that in y, if I expand that y around x, I get this term and this term. Another term, if I tried to write, would have had 1, 2, 3 thetas, and it wouldn't have been there. That's why it's not there. Likewise, this is the last term, theta theta f of y, but theta theta f of y is the same as theta theta f of x. Because if I expand y about x, I would have got one more theta and it would be killed. So you have to get used, if it's new to any of you, you have to get used to doing these kind of calculations over and over again, so that by looking at this you can say, I know where all these terms come from. Good. Now, what do we have to do? This is phi. So phi dagger is similar. I don't know if I actually wrote down phi dagger in my notes. Okay. So the first thing we can do is simplify this using an identity that I introduced last time. So phi stays where it is. The first term can't be simplified. Theta sigma mu theta dagger del mu phi. This term can be simplified. Do you remember what identity we used last time? Yeah, this is theta theta, thank you. Theta dagger, eta mu nu, which will contract this del mu to make a box. So it will be, with all the signs and factors right, it is minus 1 by 4 theta dagger, box of phi, plus root 2 theta psi plus I by root 2 theta del mu psi sigma del mu psi sigma mu theta dagger. I think all I have done here, I'm not very happy about how this root 2 is occurring. Does this look reasonable? Yeah, because what I've done here is, to go from here to here, I've rearranged the theta sigma mu theta dagger, theta del mu psi into theta theta, and then the theta dagger goes with sigma mu psi. And that's again an example of what we call the Fiat's rearrangement. I don't know if you've heard this word, but Fiat's rearrangement is the term given typically when I have two bilinears in fermions contracted, A with B and C with D, and then I rewrite it as bilinear A with C and B with D. Okay, so there's a set of rules for that. In general, they are linearly dependent. So you have many possible bilinears with or without sigma matrices sandwiched and all. There are rules to give you one set in terms of the other set. Okay. But as people realized last time, in these examples, because we're just working with two component spinels and there isn't much to expand out, the best way to see that this is equal to this with the change of sign and the new factor is just to expand out this in components, expand out this in components and compare it. As simple as all that. Okay. So this is good. This tells us phi. Now let's write phi dagger. I'm really doing this in painful detail, but I don't think it will hurt. Okay. So phi dagger comes out to be phi star of x, everything is of x, then plus I theta sigma mu theta dagger del mu of phi star minus 1/4 theta dagger box of phi star plus root 2 theta dagger phi dagger minus I by root 2 theta dagger theta sigma mu and finally plus theta dagger somehow I lost that term here, didn't I? Didn't write it.
Theta psi term.
1 second. Yes.
Sign will be changed.
Good. Exercise for you. Please tell me this afternoon by 4 o'clock whether this is correct or not.
No, the term before that.
What one? This one?
Yeah.
You're saying that when I conjugate this, I get this one. I don't get this one. I get a minus sign. I explained this in gory detail in my first lecture on two components. Go back to your notes. Actually, that might have been a lecture you missed, but you have to work this out. I'll tell you the answer. When you complex conjugate a bilinear, it goes the other way, but the rule for contracting undotted spinors is that this is raised and that's lowered. The rule for contracting dotted spinors is that the first one is lowered and the second one is raised. And since the that's bothering me now. First is raised and second is lowered for undotted, right? Second is lowered for undotted. And so when we complex conjugate, we get, so we have theta A psi A star. Yeah, correct. So we get psi A star theta. So the first thing is that when you conjugate product of two guys, they get reversed. That's always true. It's the way we do it with matrices. Okay. Now we realize that this is psi A dot dagger, theta A dot dagger. Which is the same as psi dagger, theta dagger. The important point is that, so this much is obvious. What's less obvious is that this is the same as theta dagger, psi dagger. That is, without conjugating, you can interchange the order of these, because when you do so, you'll get a minus sign, as well as then you have to raise and lower the indices oppositely and you'll get another minus sign. So there are two identities involved here. One is that daggering theta psi gives psi dagger, theta dagger, but the other is that theta psi is the same as psi theta, not opposite of psi theta, and that's because of the index contraction. Okay, good. So we've got this. So now we only have to multiply phi and phi dagger and then integrate in d2 theta dagger. Do people see any shortcut for doing that? I have to multiply this long thing by that long thing, and then I have to integrate in d2 theta dagger. Thank you. We only have to look at the for theta terms, and therefore for purposes of our discussion, phi dagger phi is equal to all sorts of stuff that we don't care about, plus theta dagger, something. And now that something will involve phi star times this guy, so that's minus 1/4 phi star box phi. It will involve phi times this guy, that's minus 1/4 phi box phi star. Then it will involve this term times that term. Okay, but in this product I'll have theta sigma mu theta dagger and theta sigma mu theta dagger, but we already know how to cope with that. And what we'll end up with from there is, I keep losing my page, what we end up from there is plus a half del mu phi star. Okay, that's part of the story. Then we certainly get f star from this and f from that. So we get with a plus sign f star. Okay. Then we get plus I by 2 psi sigma mu del mu psi dagger. Now I'm just going to write this all out without explaining everything. And actually we'll get another term with a minus sign and the del mu acting on this side. So I can just put this double-edged arrow, and that's all we'll get. Okay. And now the nice thing is, here I partially integrate one del onto this, so it changes the sign. Here I do the same, it changes the sign. I add up plus 1/4 plus 1/4 plus half, and I get plus 1 precisely. So this is equal to del mu phi star plus I by 2 psi sigma mu del mu psi dagger plus f star, and this is the result that I claimed at the beginning of the lecture. Okay. The last step of integrating out d2 theta dagger, because of our clever choice of normalization of that measure, makes this exactly 1. Okay. So now, I wish I had the equation I had written in the beginning. We have to take this kinetic piece, add it to the contribution from yesterday. So this is the kinetic jump. We have to add it to the contribution from yesterday and integrate out f. And that's the only part that I'll focus on. So f dependent terms. Notice that I use the letter f in two different ways. An f term is the d2 theta integral, but here I am talking of the f field itself, okay, which is the f term in the chiral superfield. And so the f dependent terms are f star. This comes from the d term of the action, d term in the action. And now we need to add to it what comes from the f term in the action, which is, as I wrote earlier, half m 2 phi f minus psi plus half m star 2 phi star f star minus psi dagger. And now the last step, this comes from the d term, from here. And the last step is to integrate out f. Integrating out a field doesn't normally mean taking its equation of motion, solving it and substituting it back. But when it's a non-propagating field which has a non-derivative kinetic term, then it is the same thing. In other words, we can take this and we can legitimately, even in the quantum theory, write that the equation of motion for f star, for example, which says, so del by del f star, putting it equal to 0. Remember, there are no other terms in f except the ones I've written. All the others that I haven't written are terms in phi and psi. This tells me that f plus m phi is equal to 0. As simple as that. If I've got my conventions right. Actually, it should say that f plus m star phi star equal to 0. Thank you. Okay. Very good. And so we use this. This solves that f is minus m star phi star. Similarly, f star is minus m phi. And we put both those in there. Okay, and then collect terms. So we insert this back and collect terms. And we finally end up with minus phi m square phi star phi minus a half m side psi plus m star.
Say why? What is this that we did? Like we wanted to integrate out f.
Yes.
And why is this equivalent to that?
We've solved its equation of motion. Classically, this is what we mean by integrating out a field. Why it's the same quantum mechanically is that the term that this gives in the functional integral is a pure Gaussian, and a pure Gaussian can be evaluated. If it's a Gaussian with derivatives, then the evaluation of that Gaussian is det of the kinetic term operator. Or det
no loops with this particle in the loop.
Well, actually that's not true. You see, if we kept this in the theory, there would be loops with this particle in the loop because we'd have vertices in which a phi can turn into an f.
Yeah, but the f cannot propagate.
It does propagate with unit propagator. The propagator of this is 1. What it is not is 1 by k square minus m square, but it's 1. So it's there. It's not that it doesn't propagate, it's that its propagation is trivial, I would rather say. Okay? So actually what we are saying, the content of the statement is quite non-trivial. That if I really was too lazy to integrate out f from this, I would have to deal with a theory where there's a field f with a propagator 1 or minus 1, more like minus 1, and a vertex in which a phi can turn into an f. That means that when phi propagates, I can put a cross there and that is like a tadpole, that it comes in as a phi and goes out as an f. Once it's an f, it can form loops involving f. Okay, and anytime it likes, it can go back into a phi, or phi rather a phi star. Okay, so I have lots of loop diagrams involving f, and I can spend a lot of my time analyzing that. However, in the functional integral, instead of doing perturbation theory first, keeping f, I can decide that I integrate out f and I do perturbation theory in the remaining part of the theory. But when I do that, then this is my theory. Okay, yes.
These lines, I mean the propagators for f don't carry any momentum or anything. So probably they can be just...
They don't carry up, yeah, they don't depend on momentum, but the momentum is still carried. Since f's are functions of x, the usual rules of field theory hold that momentum is conserved at a vertex. By the way, you will be hard pressed to find any vertices here because I am doing free field theory. Right now it's only propagators and mass terms, but mass term is a trivial example of a vertex. You won't be able to make too many loop diagrams out of this kind of thing, except disconnected ones. But we'll generalize this structure to interacting theories. In those theories, you'll see that f can transition into a function of phi. That means that there will be a vertex with an f coming in and let's say 2 or 3 phi's going out. So that's there. Okay. Then there will be certainly Feynman diagrams. F will propagate in loops. F will depend on, there will be a loop momentum. It will be conserved at vertices. The only thing is whenever you see an f propagator, you don't write 1 by k square minus m square, you just write 1. So that's the f problem.
But as long as there is no external f state, f will always get integrated out.
Yes, f will always get integrated out means what? We have to count all the diagrams with f occurring in all possible ways. Integrated out has to be done before you define your perturbation theory. Perturbation theory is around some free theory. Actually, another way you can say it is that this term is linear in f and linear in phi. So it signals some kind of, not exactly instability, but bad definition, because an f can turn into a phi or a phi can turn into an f. Okay, so you like in some way to re-diagonalize the theory. Okay, and if you re-diagonalize the theory by shifting f such that ff star plus phi f turns into a new quadratic term and then some phi star phi, then you will find that the new quadratic term in f decouples from the theory completely, and then its Gaussian integral is 1. That's perhaps the best way to think of it. Okay, there are many alternative ways, but the general rule is that when a field appears in a field theory without any derivatives on it, so that means its entire occurrence in the field theory is non-derivative in nature, then it can be integrated out. And there is an equivalent field theory which, okay, so here's another statement to add with. You can also integrate out a field with derivatives. You could integrate out phi from this theory and end up with the theory depending only on psi, even the interacting theory. And it would be supersymmetric, that wouldn't be the problem. It would be non-local. It would be non-local because the thing you've integrated out has got derivatives. And so the effect of integrating it out will have inverse of those derivatives all over the place. So the effective Lagrangian will have things like 1 over derivative or 1 over box in it. That's a non-local Lagrangian. Such non-locality can't occur when you integrate out a field which has no derivatives in its kinetic term. So here's another way of saying it.
How F will change in phi when they have different dimensions?
How F can change into phi when they have different dimensions? Because of M.
Yeah.
So M phi and F have the same dimension.
Yeah.
But I mean, you shouldn't worry too much, right? I mean, photons, electrons and positrons turn into photons without having the same
I have to
dimensions.
see that spin is somehow.
Spin. They are all scalars. Phi and F are both scalars.
Yeah.
Yes.
Yeah.
There is no issue of spin. And the requirement about dimension is not that they should have the same dimension, but that the total dimension of this should be 4, including the interaction, including the coefficient. This is 1 plus 1 plus 2. Psi bar gamma mu psi times a mu in electrodynamics has dimension 4, but psi and a mu don't have the same dimension. Okay. Good. Well, I'm glad there was some discussion because it suggests that this was not completely trivial. Anyway, so our bottom line here is that I hope you can put the patchwork together. The D term phi dagger phi eventually produces this piece. This is a conventional kinetic term, this is a conventional kinetic term. This is an odd thing which we have to pair up with stuff coming from the F term and then eliminate the F field. Okay? And at the end of the day we get back conventional mass terms. So the final theory, if you assemble it, is a conventional kinetic term for phi and psi and a conventional mass term for phi and psi and nothing else. Okay, so that's exactly the theory I wrote down 2 lectures back. I started introducing supersymmetry by saying there's a theory of phi and psi where I can find supersymmetric transformations. Okay, so there's a new invariance, unexpected invariance of it, and now I've reconstructed for you the same theory through superfields. Exactly the same theory. We also learned, therefore, that the chiral superfield capital phi, which has phi as its first term and psi as its second term, really that's its full content physically. The F, which is its third term, is really not physical. Okay, I can't resist making one more comment there about the role of F. One may worry why F had to occur at all if it wasn't going to do anything. And it's actually more important than we think. So let's just understand the role of F briefly. So recall that phi was phi plus root 2 beta psi plus beta theta. Okay. All these are functions of y. So that's okay. Let's count degrees of freedom. Okay. Degrees of freedom count over here tells us that this being complex are 2 bosonic. This being 2 component complex are 4 real fermionic, and this being complex is 2 and bosonic. So therefore the degrees of freedom contained in a chiral superfield are 4 bosonic and 4 fermionic. Okay. However, this is really properly called the off-shell degrees of freedom. Off-shell is a word which means when the equations of motion are not necessarily satisfied. We didn't impose any equation of motion on this, we just counted degrees of freedom. This is how you count off-shell degrees of freedom. In an off-shell count, the photon has how many polarizations? 4. So this is that kind of counting. Okay. We know that the on-shell counting is reduced. So the on-shell degrees of freedom, the way that works is that just following these vertically, the scalar field even on-shell still has 2 bosonic degrees of freedom. Okay, so even after it satisfies its equation of motion, there are 2 bosonic degrees of freedom. With the fermion that's not so. After it satisfies the Dirac equation, it gets reduced to 2 fermionic degrees of freedom. Okay. A wild fermion, if you like, if you think about it that way, purely left-handed and spin up or spin down. Okay. Spin up left-handed, spin down right-handed. If you think of it as Majorana, then it's not got a handedness, but it's real, and then it has a spin up and spin down. Whichever way you look at it, the on-shell degrees of freedom of a fermion are 2. So it's been reduced. And on-shell means applying the equations of motion. So the on-shell degrees of freedom of F are none, because we can remove it from the problem. And we see that the degrees of freedom are 2 bosonic, 2 fermionic. And what you learn from this is that in a supersymmetric theory, the on-shell degrees of freedom match, of course, because supersymmetry transforms bosons into fermions, so they must match. With auxiliary fields like F, the off-shell degrees of freedom also match. Okay? If F wasn't there, the off-shell degrees of freedom would not have matched, but the on-shell degrees of freedom would still have matched. Okay? What happens is that with on-shell degrees of freedom, that's what really your physics is concerned with. But in the full quantum theory, off-shell degrees of freedom also propagate. Even then, ignoring F would still give you a consistent quantum theory, but you would not have manifest supersymmetry, because ignoring F, you would have 2 of these and 4 of these, and you would have to keep doing something to see the presence of supersymmetry in the theory. So the auxiliary lesson of all this, auxiliary fields are important for manifest supersymmetry. And we'll see this happening in the future. We'll see how this phenomenon affects us.
This is also manifest in superspace.
Yeah, thank you. So the whole point is, remember, we never discovered this auxiliary field till we went to superspace. When we found supersymmetric theories in ordinary space, we didn't find the auxiliary field at all, right? We just had an action with phi and psi. So historically what happened is, people who tried to write supersymmetric theories in ordinary space just thought, okay, let's match on-shell degrees of freedom, so let's propose a phi and a psi, and let's try to write some invariant action. That worked. But then when people said, okay, it must be all manifest in superspace, that's why we invented superspace, this is Salaman's strategy. Then of course they found that this thing is there, you can't possibly get rid of this by imposing any constraint on phi. Already we got rid of lots of things by imposing the chiral constraint, but we still have this. Then they said, okay, how does this reduce to an ordinary Lagrangian? So they got the one I wrote. Then they said, F is an auxiliary field and it can be removed from the theory. So we are back to the original theory. But as long as you are in superspace, F is always there. It's only when you go to ordinary space that you can remove F. And the reason is this line. Supersymmetry is manifest in superspace by construction. Superspace is that space in which supersymmetry is manifest. So obviously F will be there.
How do you do counting in superspace?
You have to count. The way you do counting is, of course, just you can't do counting of the superfield. The superfield automatically has an equal number of bosonic and degrees and fermionic degrees of freedom. There's nothing to count. Okay. If you want, the point is that the superfield is itself a boson, if you like, but since it depends on theta, it contains ordinary fields that are fermions. Okay, theta times psi is a bosonic field, if you like. This language. That's because theta is anti-commuting and so is psi. So only when you break up phi into its components and count the individual components, which amounts to going to ordinary space, then you see the match of bosons and fermions. In superspace, all you see is that there's an action and it's invariant under varying phi by I epsilon q times phi.
So this time all for n equal to 1 supersymmetry.
Everything I'm saying in this entire course is only for n equal to 1 supersymmetry.
So higher if you look at n equal to 4 supersymmetry or some such thing,
Yeah.
it's not clear there's a super reformulation.
Oh, that's the problem. I shouldn't spend any time on this, but since you asked, the whole problem with n equals 4 super angles or n equals 8 supergravity is that we don't know the complete auxiliary field structure, and knowing that or knowing the superspace formalism is the same problem. It's an unsolved problem, but there should be a superspace in which the auxiliary fields are contained.
But should there exist one? is it obvious if there is
No, it's not
truncation of that
No.
because
No, it's not obvious.
but the n equal to 1 truncation that will certainly exist because
N equals 1 works fabulously in superspace. Not only that, many important things that we would like to prove about N equals 1 supersymmetric theories can be proved most easily or only in superspace.
Right.
Superspace is fantastic for N equals 1. Since N equals 1 is all we care about for LHC.
No, that is
Is it on the d4x and d4 theta? So
d4x and d4 theta. I mean that's an interesting point. He's saying that does superspace exist for N equals 1 because there's d4x and d4 theta. Actually no, in two-dimensional supersymmetric theory you can have d2x and d4 theta or you can have d2x and d2 theta. Both are very well defined, both have superspace and both work very well. So it's not any requirement that the number of thetas must be the same as number of x's. In supersymmetric quantum mechanics you only have a t, but you can have any number of thetas essentially. Yes. Yeah. Why do I say that we only care about N equals 1? Thank you. So, assuming that I finish in today's lecture this stuff, the formalism of supersymmetry, my next lecture I'll start by explaining why we are discussing supersymmetry at all, because that's not the title of this course. It's called LHC for string theorists. My claim is that the only form of supersymmetry which might be relevant, by the way, it's not guaranteed to be, but it might be at LHC, is N equals 1 supersymmetry. There may be no supersymmetry or consistent with what we know about physics. There could be N equals 1 supersymmetry broken and it could be found at LHC. And I'll explain all that. I mean, that will be part of the motivation for this course which I haven't given yet. So I'll give that in the next lecture. By the way, please don't allow us to disperse before discussing the date of the next lecture because next Monday, Tuesday, Wednesday is the review of this department and so there's no possibility of having any lectures. Okay, so we have to have it later in the week if at all. Good. Now, all this is very fine, but why in a practically oriented course did I bother to teach you superfields at all? Okay, it was a hard thing to have done, but there's an immediate payoff, and the payoff I had already promised it implicitly that once we've learned about superfields, writing the interacting theory, most generally interacting theory, will become very easy. We've only done a free theory so far. What's the most general interacting? It's almost obvious what's going to make this easy. Was there a question? It's pretty obvious why it's easy. It's easy because we've just seen that the only possible ways to write a superspace action are D term and F term type action. Okay, so we're going to do interacting theories involving phi and phi dagger only. We haven't said that phi and phi dagger are the only type of superfield, but assuming that it's the only superfield, then we'll write interacting supersymmetric theories. Okay. There's an obvious way to see that this can't be the only superfield around because we notice that there's no gauge field incorporated in this phi. It only has a scalar and a fermion. So we cannot make a supersymmetric standard model just out of phi and phi dagger. Okay. However, since I'm discussing interactions, it makes sense for me to put an index I over here which goes over any number of fields. At a later stage I might specify that this I is an index according to which these fields transform in some SU2 or SU3 or some other thing. But right now I'm just saying that let's imagine a system with some number of fields, not necessarily one. Okay, and let's write the most general interactions. So here's the most general D term. It's actually painfully simple. It has to be like this, and it has to be a function of phi and phi dagger of all of them. And that's the answer. Any function of phi and phi dagger, as long as it's real. obvious that this is going to be supersymmetry invariant? For the general proof of supersymmetry invariance, I will come back to it and we will see that it is obvious. Okay. All you really need to know is the following. Phi is a chiral superfield, so it transforms in a particular way under supersymmetry as I epsilon q phi plus epsilon dagger q dagger phi. Okay. Phi dagger transforms in the opposite way. Alright. When we transform both of them, so each of these is not invariant, but when we just made a product phi times phi dagger, and we found that after integration in d2 theta dagger, it is invariant. Okay, we'll see that it's a very general property, and it should be so because the whole point of constructing an invariant Lagrangian is to take covariant pieces and put them together. Okay, so I claim that this is always invariant for any choice of k. Secondly, the most general, I'll prove it. By the way, I'm just saying this now. I will give you the proof in a second. What's the most general f term? Well, for an f term, I have to take d for x. Then I have to take d2 theta and put in a function of phi's only, which doesn't depend on phi daggers, right? So I'll give a name to that function. I'll call it curly w of phi's. Okay, and then I'll add the complex function. Finished. Going to give you a proof of the independent supersymmetry invariance of this term and this term. However, you need to remember a few things. If you want to reduce this system to ordinary fields, I'll have to take this and expand out the content in terms of phi, psi and f. Okay, and I would hope that this function k will be sensible enough that there is a quadratic term in it, phi dagger, plus could be lots of other things. Okay. In that case, the quadratic piece will give me a kinetic term. Alright? But there will certainly be dependence on the auxiliary field f coming from here. When I expand this out, I'll get potential like terms in phi, psi as well as f. Finally, I have to add them and only then eliminate f. So f, if you like, the auxiliary field f is the link between this and this. I can't really go to ordinary space until I've added these two and then integrated out f. I can't first integrate out f because f occurs in both and it's the field I want to integrate out, so I have to first add them. That's clear, right? Okay. Now, question? And the non-interacting?
This is just the interaction.
No. It includes everything. That's why I said. So okay, let me give some names. This goes by the name of scalar potential, and this goes by the name of super potential. These are just names for now. Important thing to remember is super potential is holomorphic, which is a fancy word for analytic, i.e. depends only on phi. While this is real, therefore it must depend on phi and phi dagger in a way that's real, yes.
If integrated on earlier and then added phi, it will make any difference? Integration and addition is
because f occurs here and f occurs here, and integrating out means I have to solve the equation of motion of f. Okay, so the equation of motion of f has to be obtained by differentiating this plus this. If from this in the free theory we had got f squared, and from this we had got f phi m. If we try to integrate out separately, this would have told us that f is 0 and this would have told us that m phi is 0, neither of which is the case. It's actually f is equal to m phi. So you have to add and then yes.
When we are taking copies of this parallel,
Yes.
then we have more than one small phi.
Absolutely.
And
Yes.
capital F.
Yes, you have lots of f's, but
You have lots of
yeah. So when you have this index I, it's inherited by all the fields. So the small phi's have an index I, the xi's have an index I, and the f's have an index I. So there's a whole bunch of f's to integrate out. Yes. So in principle, it could be a hard job to actually solve the equations of motion of f. Okay, but okay, that's a technical problem if and when it arises. Conceptually, it's not much of a problem. Okay. So I've given you this grand claim and 2 comments on it. One, so first of all, let's remind you that K of phi I and phi I dagger equals phi I dagger phi I. If I choose this special case, and W of phi I equals half m phi I squared, gives me the free theory. This is a theory that we've already spent last lecture and this lecture discussing. So it's a special case. All I am proposing now is to let K and W be anything instead of be these particular values. However, if we hope for this field theory to have a sensible perturbation expansion, then in some suitable choice of fields, both K and W should have quadratic terms. Just like in any ordinary field theory. Okay. Nobody stops me writing a classical Lagrangian which has only del mu phi to the 25. Okay, but then that doesn't have a conventional propagator and it doesn't have a perturbation theory. Likewise, if I don't write a mass term, if I have a potential which starts with 5/4 and no mass term, what should I expect? Nothing inconsistent about it, but I would expect that. If I wrote a potential in an ordinary field theory which started at 5/4 and didn't have any mass term at all, what would I expect? Why would that not be natural? I don't think, unstable in the sense radiative corrections would generate a mass term unless there was some reason for them not to do so. Okay, so it would be a very specific unnatural choice unless there was some symmetry involved in the problem. Okay, so in general, a general superpotential ought to have a mass term unless there's some reason why it shouldn't. And a general scalar potential ought to have a quadratic term anyway, otherwise there's no perturbation theory at all. Okay. But,
in electromagnetic, because the symmetry doesn't have it.
That's right. And but indeed that symmetry clearly is not here because we don't have gauge fields. Okay. So this is just an expectation. This is the free theory, this is an obvious statement. And our expectation is that we'll be able to think of these terms as having pieces like this plus other pieces, whatever they may choose to have. We'll also see what's the most general renormalizable such term. That's another story which we haven't come to. Okay, we haven't imposed any criterion like that because this is all classical field theory. Now the all important question is how do we show supersymmetry of this thing? So this is comment 1, 2. Supersymmetry invariance is trivial okay, so here it is. Okay, so any superfield f, okay, I think I can even prove this for you. F of x, theta and theta dagger has the property, this I can prove. Actually, I think this is a much better way. That delta f under SUSY, which is I epsilon q plus epsilon dagger q dagger f, the whole superfield. Okay, this is equal to, in ordinary space, lots of terms plus theta, theta, theta dagger, del mu of something. That's all we need. Okay, and I'll prove this statement to you. Once I prove this, I hope you'll agree we are done. Because it means that if I integrate d2 theta dagger of this f, all these terms I can ignore. This last term gives me a total derivative, and then when I integrate it in d for x, I get 0. Why is this true? This is true because look at the constitution of q and q dagger. They involve either del by del theta or del mu. Okay. Now, del by del theta has the property that whenever it acts on f, it reduces the number of thetas in a given term. Okay, so the 4 theta term will become a 3 theta term, 3 theta will become 2 theta, 2 theta will become 1 theta, and so on. Right? That's the effect of the del by del thetas inside Q and Q dagger. Okay, but then if I've acted with that, then I won't have any d term left. Okay, because after acting with del by del theta, I can't generate a term with 4 thetas because it would have been generated from a term with 5 thetas, which there isn't. Okay, so I can already neglect the del by del theta and del by del theta dagger part in here. Everything else is del mu part. Okay, it comes with thetas, which means what it will do is it will take a 3 theta term and multiply it by another theta and a del mu. It will make it a 4 theta term with a del mu. Right, here's the proof. Okay, so this is a very general property of all superfields. Do people want me to repeat the proof? The proof, I'll write it here. Del theta dagger in Q never generate d terms because they always reduce the number of thetas inside the superfield, so they'll never generate a 4 theta term. And the second part of the proof, which I won't even write, is that once you ignore the del theta and del theta dagger, the rest of Q and Q dagger is del mu. Okay, so whatever it generates has got del mu. Okay. There will be terms which are not the last terms here we don't have del mu, but then they are killed because I am going to integrate this in d for theta. So one way or the other, everybody gets killed.
Why did we use the fact that k was a real function?
Yeah, actually we don't need it. I'll just prove that we don't need it. Thank you. So that isn't even valid. Okay. Now
Did we choose it to be real?
we chose it to be real because it's the Lagrangian of the theory. It's a good reason. W we didn't choose to be real because W is a chiral. W is the f term, and f term is always integral d to theta times a function of some function plus its complex conjugate. So that's always real. So W doesn't have to be real, and in fact, built into the structure of W, it's very naturally complex. You'll see that most W's that we ever deal with are complex. Actually, it's trivial. W is only a function of phi, so it has to be complex. It's an analytic function of a complex variable, so it has to be complex. There's no choice.
So the only condition on the Lagrangian is that it has to be a real.
Yeah, that's the result. So we are only imposing that the Lagrangian is real and that it's supersymmetric invariant. And of course Lorentz invariant and all that, because if it's supersymmetric invariant, it will be Lorentz invariant because supersymmetry algebra, which I haven't gone into in that much detail, implies the Lorentz algebra. So we don't even need to worry. Yes.
I mean, this F superfield in a Lagrangian will have like powers, like square or something.
Of what? Of ordinary fields. Yeah, it can have anything.
No, I'm saying just like phi square appears in the Lagrangian.
Yeah.
So this F, curly F will
Yeah.
also appear like in square or other forms.
Yes.
There, can you show then the full product of everything will be
No, but that's another general.
It's another superfield. That's the whole point. F is okay. So here I should actually mention one thing which I wanted to say earlier. We should not confuse between a fundamental field and a field. Okay, a fundamental field is like phi and psi and f in this field theory, but phi squared or phi times del psi or anything are all fields. Okay, and the whole point about superfields is that any product of superfields is again a superfield because a superfield is only a function on superspace. Obviously, if I multiply 2, I get another function on superspace. Okay, so this is being applied to the final answer. And actually, this is something I think was very smart about the supersymmetric people when they started working on this subject, that they realized at once from lessons in elsewhere in field theory. These were people who are really very good in field theory. That you can apply the same logic to a field or to a composite field to an entire Lagrangian. Okay. Later, Seiberg had the insight that you can even apply the same logic to the coupling constants. So, in fact, in many of his proofs about non-renormalization theorems, he decided to treat M, the mass, and G also as superfields. You can formally do that. Okay? It's a bit like Unix where everything is a file. Okay, your printer is also a file. It's a bit like that. Okay. Now, so in this particular case, it's applied to the entire D-term Lagrangian. So F for this discussion is K. However, I've only proved this for a general superfield. Now, for a chiral superfield, we have the same exact property. This time, let me call it G, and it's a function of y and theta. Okay, then delta G under Z is again this. And this time we have to be a little bit careful because G has this dependence on y as well as on theta. Okay, so these things can act on all of those. Nevertheless, it remains the case that this only generates plus theta del mu of something. I'll leave this to you as an exercise. Okay, an analog of that theorem but applied to the last term of the chiral superfield. The theta.
Write the G of y and theta is G of x theta theta y. It will be redundant.
No, that doesn't help. That actually hurts. Because then differentiating the third term might bring about a new term here. Supposing I differentiate in theta dagger, a term theta dagger. If I allowed for it to be a most general superfield, then this isn't true, right?
We want theta.
We want only theta. Now the way out, of course, the simplest way is to realize that under integral b for x, I can replace y inside this field by x, and then this is obviously true. Okay. Another way is to notice that the third and fourth order terms in theta have a special form because of the dependence on y and theta, and that special form still prevents us from generating non-derivative terms at this order. There are many ways to do it, but anyway, it's a fact. Okay. And here you notice one of the very pretty things about supersymmetry. Notice that what would have been here in this superfield is its F term. You see that F has a meaning beyond being a particular auxiliary field. F term always means last term in any chiral superfield. There's a similar name for this theta fourth term in a general superfield. It's called the D term. Okay. We've seen a role for the field F in the fundamental chiral superfield. Now we see the more general role that any chiral superfield, fundamental or otherwise, its F term always transforms as a total derivative. Okay. So it's kind of a slogan. F and D terms of any, of course this applies to chiral, general, so F/D terms of any chiral general superfield transform into a derivative under SUSY. Here's the slope. We just proved it. Okay, I hope people got that crucial point here, which is that since we are going to ask for this to happen under integral d for x, and this is chiral, we can really replace y by x. And after we've done that, then this terminates at order theta, and then these guys, the del by del theta parts will give us lower order in theta, and the del mu parts can give us this, but then with the derivative. So this is the proof. Okay. And this immediately proves invariance of all D term and F term actions. You see how simple it is. So this is really the payback from all the work we did to construct the superspace formulas. Now, unfortunately, I have quite a lot more to do, and I have only about 10 minutes. But let's see what we can do in those 10 minutes. Are there any questions up to now? I hope you are seeing, as I said, we will get to more phenomenology soon, but I hope you are seeing how beautiful the structure is and how inevitable it is. There There are technical difficulties, it's not something very easy, but once you accept the idea of superspace and supersymmetry, everything I've done is very natural, and I think people are very much motivated by the fact that here is a symmetry which the only one path after gauge symmetry, which can be naturally implemented into a Lagrangian and has some very obvious symmetry properties that it's easy to make a Lagrangian that's invariant. I should go further. If I did with this, I haven't finished what I was going to do. I have to expand out these Lagrangians and show you what they look like in open space. If I go further with this and I do perturbation theory like Feynman diagrams in superspace, okay, then all renormalization effects, all loop effects, anything I calculate will be expressed in terms of superfields. So starting with an action in superfields, the effective action obtained by doing Feynman diagram will also be in superfields, also in superspace. Therefore, supersymmetry will be present throughout. Okay. So in that sense, unless something is wrong, seriously wrong with superspace, or there's some anomaly in discussing superspace, supersymmetry cannot get broken, cannot be anomalous if this formalism makes sense. Okay. Moreover, at every stage of the formalism, we'll see the supersymmetry being present. That's another nice thing. Yeah, so actually what I should do today, I forgot that this had to be done, is to take the most general action I wrote for you and tell you what it looks like in ordinary space, because much as we like superspace, we understand our physics in ordinary space. So the question is, what is this? And what is this? In terms of ordinary fields. And what we can say without doing any calculation is that it's going to give me a theory involving a complex scalar, set of complex scalar fields phi I, set of fermions psi I, and a bunch of auxiliary fields which I hopefully can integrate out. So the answer is, I'm not going to write it in excruciating detail, but I'll just show you how it happens. Okay. The first thing is that when you expand this out, you'll find that the answer depends on the second derivative of K, of the Taylor potential. And in particular, you get a term K, comma, I, J bar of phi and phi star times del mu phi I, del mu phi star J. Lots of other terms, but here's one term. Does this look reasonable? First of all, if there was only one field and K was just phi dagger, then this thing would be 1. That's the kinetic term we looked at before. Okay. So my claim is that more generally, when I try to do this integral on K of phi and phi dagger, all I need to do is to differentiate K once in phi and once in phi star, and then with this function contract this, and of course then there will be terms which are similar involving psi, and there will also be a term that's similar involving f. Okay. The question I want to ask you is,
this comma I j bar is with respect to capital phi?
yeah, and then evaluate it at small phi. So you can you can take the function k, evaluate it on small phi's, and then differentiate it in. So these are all the phi's, of course, and then differentiate it in phi I and phi j bar. Has anyone seen a field theory action looking like this before, and do you know what it's called? Yes, it's called a non-linear sigma model. Okay. And in the non-linear, what is the meaning of a non-linear sigma model? It's like a generalized kinetic term for a set of scalar fields, but with a non-trivial metric in the space of those fields. Okay. And in fact, if you take this thing and drop all the space dependence and think of this only as time, then k I j bar phi dot I phi dot j star is the Lagrangian for a particle moving on some complex manifold. So this is the generalization of mx dot square, where the manifold, this is non-relativistic quantum mechanics, just have a manifold instead of flat space. Okay. Now complex is crucial. These fields are complex and this K is differentiated in I and J bar. And therefore, we have a nonlinear sigma model where the metric in this complex space parameterized by I and I bar, which is the space of fields, has the property that it is G I J bar, which is given as K comma I J bar. Okay. And that means that although the metric could have had components Ij as well as I bar, J bar as well as Ij bar, could have had all kinds, it only has the components Ij bar, the mixed components. Okay. And such a thing is called a Hermitian metric on a complex manifold. And if it's writable in this form, it's called a Kähler metric, and the manifold is called a Kähler manifold. This is an old result from complex differential geometry predating supersymmetry by on the order of 100 years. Okay, this is the definition geometrically of a Kähler manifold. All you have to do is forget that this depends on fields and just let it depend on the same number of coordinates, but complex coordinates. Okay. A Kähler manifold is the most natural type of complex manifold there is. By the way, ordinary flat complex plane is an example of Kähler manifold, and you know that in the complex plane, the metric is dz bar. There is no term in the metric dz squared nor dz bar squared. It's only dz bar. You see that it's of this form. What is the Kähler potential for flat space? Zz bar. That's all. Okay. What's the Kähler potential for free supersymmetric theory? Phi dagger. Same statement. Okay. Therefore, in free supersymmetric theory, the metric will come out to be 1. Okay. If the metric is 1, then we only have this, and this is the free kinetic term. If the metric is other than constant, then it may have a constant piece, but then there will be terms higher order in these phi's, and so we have interaction terms in field theory, but which are of the form many phi's times one del phi and another del phi. Okay. Such terms, by the way, are all non-renormalizable. I hope that's clear, because phi has canonical dimension 1 in 4 dimension. This already has dimension 4. The only thing here that gives a renormalizable theory is constant. But we won't only be interested in renormalizable theories, because effective field theories need not be renormalizable, but they still have to be supersymmetric. And we'll see that in such effective field theories, these things do get generated. Okay. Now, Kähler manifolds have many nice properties, which I can't go into, but there's one property that's particularly pretty, and that is that, well, first I should have said, notice that for this to be possible, the metric must satisfy an integrability condition. If I take a metric and Gij bar and differentiate further in K, another field phi K, or another coordinate, this must be equal to Kj bar I. Okay. That follows from this, because if I differentiate once more in K, then here I am differentiating in I J bar K. 3 different derivatives, but then I and K derivatives will commute because they are only derivatives. Okay. So this is an integrability condition for a metric. In other words, if I find a metric which satisfies this condition, as well as the complex conjugate condition that I J bar L bar is I L bar J bar, meaning differentiate in the conjugate variable and then interchange. Okay. If it satisfies this, then locally I can always write it like this. I hope that's clear. Okay. But now a very beautiful fact, K is not uniquely defined. That is, given a metric, I might find one K which satisfies K Ij bar is Gij bar, but I can find other Ks very easily. Can you guess how? I can add things to K which won't change its derivative in Ij bar. Holomorphic or anti-holomorphic. And since K is real, now you see why K is real, by the way. The metric has to be real. even in a complex manifold, the metric should be real. That is, if I star it, I get the same thing as this with I and j bar interchange. That means k has to be real. Okay? But I can take k of z and z bar and send it to k of z and z bar plus a function of z plus the complex conjugate of that function. Okay? And if I do this, the metric doesn't change. That I think is clear. Okay? Well, what does it amount to doing in that action? Yeah, I take the scalar potential and I add to it a chiral superfield plus an anti-chiral superfield. Okay, and why doesn't it change the action? Because integral d2 theta dagger over a chiral superfield is 0. Because the chiral superfield doesn't depend on d2 theta dagger, the anti-chiral doesn't depend on theta. So that means that in the supersymmetric theory, the scalar potential is ambiguous or undefined up to the addition of a chiral plus anti-chiral superfield. That's very beautiful fact. Okay? You can see it right from there. Good. So, with that, I've shown you that the scalar potential piece in a general interacting Lagrangian makes it a sigma model, and then there are modifications to the fermionic terms very similarly. Okay, also involving the second derivative of k and some covariant derivatives and so on. I really don't have the patience to write it all out, but you can see that in principle it's doable. Okay. If you can actually start with this and derive this term, which would be no more than 5 minutes, then you're on your way. Then you can derive all the other terms also. Okay. It's only as easy or hard as doing the kinetic, the free case that we did already. Fine. So that's done. I will be doing something more general later on, so I probably will come to this later on again. But first, I want to finish. What's the answer for this one in ordinary fields? The superpotential. Okay. And here the answer is extremely simple. I get, first of all, I get something involving auxiliary fields F. Okay. But if I eliminate, so now I'm going to give you the answer assuming that the kinetic term is free. It's flat. Okay. Then the more general answer is also very easy. You find that after elimination of F, if the kinetic term is flat, then of course it's F basis FF star, so it's easy to eliminate F. We get minus W comma I, this is the superpotential, mod square, minus a half W comma Ij psi I psi j plus complex conjugate. Okay. Notice that when W gets differentiated, it has to be differentiated only in indices of I type and not I bar type, because it doesn't depend on I bar anyway. Okay. And now I hope you can see that if W was chosen to be a half m phi squared, okay, special case, W equals a half m phi squared and we have only one superfield. Then W comma I is m phi. The mod squared makes it minus m squared phi star phi. That term. W comma Ij is just m. Yes. So minus a half m psi psi plus m star phi star. As expected. So the generalization of this is this. We find an ordinary potential as well as we find a term coupling scalars to fermions. What is such a term called? Yukawa coupling. Okay, but we find them linked. The potential and the Yukawa coupling both come out of the same function domain. Okay, so we find a correlation between the scalar potential and the Yukawa coupling. So these are all hallmarks of supersymmetry. Okay, the most general exercise we'll do next time. We'll have to do expression for fields next time, and we'll complete this story. Any questions?
The other question is probably related to vectors.
Yeah.
So in the phi plus parameter that you can add and hold mention.
Now, phi Laplace parameter, let's discuss when we come to vector superfield, because I haven't even said what it is now. Okay.
Date of next time.
Yeah, so let's put up the camera, please, and then we'll discuss the date of the next lecture.